Hello again, and welcome to our lecture on trigonometric equations. Last time we saw trigonometric identities, and these were equations that were true for all values of x. Today we'll look at identities that are not true for all x. They're equations, and for some x values they'll be true, and for others they'll be false. Let me give you some quick examples. Cosine x equals 0. Okay, that's not true for all x, of course not. But there are some values of x for which that's true. For instance, pi over 2. Cosine of pi over 2 is 0. How about sine x equals a half? For some x values, it's true. For others, it's not. In fact, we'll solve that problem in a moment. Here's a more complicated one. 2 sine squared x minus sine x minus 1 equals 0. Looks pretty scary, doesn't it? But we'll solve that problem. We'll find the x values that make that a true statement. And then we'll also look at some of these equations where we actually can't solve them algebraically by hand. We'll have to use a calculator or computer. An example such as x equals 2 sine x. I'm not exaggerating when I say these play a very big role in calculus courses. Over and over again in a calculus course, you're doing some problem involving fancy calculus skills, and you end up with some equation. It might be a trigonometric equation, it might be a logarithmic equation, etc., and you have to solve that equation. So needless to say, success in the calculus course depends on being able to solve these equations. In fact, I'm not exaggerating when I say the calculus skills are often pretty easy. You do some calculus, and trust me, it's not so hard. But then you end up with this equation, like the ones I just talked about, and you have to solve them. Ouch, that's pretty hard. Pre-calculus is difficult. I'm not being facetious here. Calculus is difficult because of the pre-calculus skills needed for success. So I'm glad you're taking this class. I'm glad you're listening to some of these videos. I hope it'll get you ready for calculus. Okay, let's begin by solving a trigonometric equation, a fairly straightforward one, and you'll see some of the issues start to come into play. Suppose 2 sine x minus 1 equals 0. Let's solve that equation. That's the same as saying 2 sine x equals 1. And if I divide by 2, I have that equation I started with, sine x equals a half. Now let's pause here. Can you think of a value of x for which the sine of x equals a half? It rings a bell. This is like inverse functions, isn't it? But in practice, people don't use inverse functions when they solve these kinds of problems. Sometimes they do, but usually they'll just think sort of abstractly. Can I think of an x value for which sine of x equals a half? Well, pi over 6 works. Sine of pi over 6 is a half. Good. But here's a deeper question. Is that the only value? Well, if you think about it again, 5 pi over 6 also satisfies sine x equals a half. In other words, the sine of 5 pi over 6 is also a half. So I have 2 solutions now. And in fact, those are the only 2 solutions in the interval 0 to 2 pi. I have 2 solutions in that interval. But now it even gets worse. Remember, these functions are periodic. So the fact that pi over 6 is a solution also means that pi over 6 plus 2 pi, the period of sine is 2 pi, that's also a solution. Plus 4 pi, plus 6 pi, blah, 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 forever. And in fact, minus 2 pi, minus 4 pi. It goes both ways. We have an infinite number of solutions, don't we? And here's how you write it. You say the following: x equals pi over 6 plus 2n pi. And we understand here that n is an integer. That's an infinite family of solutions. And then we have 5 pi over 6 plus all of its multiples of 2 pi. 5 pi over 6 plus 2n pi. So that simple little equation, sine x equals 1/2, has a complicated looking solution, doesn't it? You can see why pre-calculus can be pretty difficult. Here's a picture of our friend, the sine curve, and I've indicated on here the horizontal line y equals a half, and you see that it touches the sine curve many, many times. I've indicated a couple of values in the first quadrant, pi over 6 and 5 pi over 6. But there are an infinite number of solutions because the sine curve goes on forever. Let's do another one. Let's do that other problem I looked at earlier that had sine squared in it. So here's the equation. 2 sine squared x minus sine x minus 1 equals 0. Let's solve this equation on the interval 0 to pi. That'll simplify things a little bit because we'll cut off the interval, a finite interval. All right, what can we do with this? Ouch. Well, you might remember that we had a similar type problem back when we did exponential functions, and we noticed that you can sometimes factor these. You can think of this as a quadratic polynomial, not in the variable x, but in the variable sine x. So watch how I factor this. I can factor it as 2 sine x plus 1 times the quantity sine x minus 1. If you don't believe me, multiply that out. If you multiply that out, you get 2 sine squared x minus 2 sine x plus sine x, and then minus 1. So it's the same thing. And the advantage now is I've converted this sum and difference to a product. And if a product of two terms equals 0, one of the terms must be 0. So let's set each term equal to 0 in turn. Here we go. 2 sine x plus 1 equals 0. That means that sine x is minus a half. And now we're back to this difficult trig question. What value of x yields sine x equal to minus 1/2? 7 pi over 6 and 11 pi over 6. Whoa. That's tough. I mean, I did that pretty quickly. I've been in this business a long time. But it's tough to come up with those values unless you're really comfortable with trig functions and the values of those common angles. So that was a tough conclusion there. Sine x equals minus 1/2 implies that x is 7 pi over 6 or 11 pi over 6. But those are the answers in the interval 0 to pi. Now I set the other term equal to 0. Sine x minus 1 equals 0. That means sine x is 1. That's pretty easy, pi over 2. So we have 3 solutions in the interval. Let's verify it with a picture. Here's the graph of 2 sine squared x minus sine x minus 1. Notice it touches the x-axis 3 times. It touches at those 3 values. I invite you to verify this graph. Take out your graphing calculator and on the interval 0 to pi, graph this function, and you'll see that it touches the x-axis 3 times. Great. Let's do one a little more interesting. And you've heard what interesting means. Okay, it'll be the function 2 cosine 3t minus 1 equal to 0. Okay, I've changed the variable from x to t to make things more interesting. So here we go. 2 cosine 3t minus 1 equals 0. Let's find all t values. This is pretty difficult, I think, but watch how we do it. Well, first of all, bring the 1 to the other side and divide by 2, and we have the equation cosine 3t equals a half. Now, I recommend the following technique. Solve these first on the interval 0 to pi, and then extend it out to infinity on both sides. So get those first few solutions on the interval, and then add the multiples of 2 pi at the end. So here we go. I need cosine 3t equal to a half. What should 3t be in order that its cosine is a half? So we're solving these trig equations again, aren't we? This is tough going. Well, 3t should be pi over 3 or 5 pi over 3. You can check that cosine of pi over 3 is a half. That's a fairly common trig value. And also cosine of 5 pi over 3 equals a half. So 3t is pi over 3 or 5 pi over 3 in the interval 0 to pi. But that's not t. T is, we're going to have to divide by 3 in a moment. But first of all, let's say the following. If 3t is pi over 3, it can also be pi over 3 plus 2 pi, or plus 4 pi, or plus 6 pi. So we write it as 3t equals pi over 3 plus 2n pi, multiples of 2 pi, n's an integer here. And in the same way, 3t is 5 pi over 3 plus multiples of 2 pi. All right, I now know all the values for 3t. What about t? Well, divide everything by 3. And you get the final answer that t is pi over 9 plus 2n pi over 3, or it's 5 pi over 9 plus 2n pi over 3. Very complicated problem, a whole lot of solutions, an infinite number of solutions. And the skills were kind of touch and go, I saw. Some tough skills there of having to solve the problem first on the interval 0, 2 pi, and then extending it out to infinity. Some advice here. You have to be totally convinced now, I think, that we have to be confident with our trig values. We have to be able to calculate the values of trigonometric functions for common angles. That just goes without saying now. I carry around these values in my head. I dream about them at night. These are values that I use over and over again when I'm teaching mathematics or doing my research in mathematics. I discover that students will come into examinations with sheets of paper with all the trig values written down, or they'll have that circle with the angles. Remember, we saw a circle with the angles of 0 and 45, etc., and they'll put down the trig values corresponding to those angles. If I allow students to bring in a set of notes for an exam, and in many courses I allow them to bring in a sheet of formulas, they will always write down basic trig formulas and values on that sheet. And of course, in our workbook, we have a list of the key values in the appendix. And so you should savor this. You should practice calculating trig functions. Now that said, some professors allow calculators. Some teachers allow calculators in the classroom. I do in many of the courses I teach. I'm not sure I'll accept a calculator answer, but I encourage students to check their answers with calculators. In fact, the advanced placement program for calculus requires that students bring a calculator to the exam because some problems can only be done with a calculator. They require a calculator to be solved, to solve the problem. And of course, there are calculators and there are calculators. Some calculators don't do much. They're kind of weak. They're inexpensive. They don't have a lot of power to them. They don't have many keys on them. And yet other calculators are really, really advanced. Every year, a new calculator seems to come out that can do more and more. And so as a teacher, you have this problem that some students are sitting there with a very cheap calculator that can't do much, and then they're right next to this rich student who's bought a $400 calculator, and hence you have to make up a test that's fair and not give an advantage to the student with the fancy calculator. Okay, enough on calculators for the moment, although in this next problem, we're going to need one. So, sometimes in these trigonometric equations, you have to actually use a calculator or a computer to approximate the solutions. In other words, you can't do them like we've been doing the previous problems and getting an exact answer. So let me show you an example of this. Suppose you want to find the solutions to the following equation on the interval minus pi to pi. And the equation will be x equals 2 sine x. So I want to know all x values such that x equals 2 sine x. Now you might try to solve this using some trig identities and logarithms and I don't know what else. Trust me, you cannot manipulate this equation to get it to look like x equals blah, 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 blah. without x. You cannot get x all alone on one side. Trust me, you can't. You might give it a try, but you won't be able to. We have to use a computer here. We have to use a calculator. We have to approximate the solution. How do you do that? Well, write it as a function, x minus 2 sine x, and graph the function and see where it crosses the x-axis. That'll be the set of solutions. Well, here's a picture of x minus 2 sine x on the interval minus pi to pi. And notice it crosses 3 times. It crosses at the origin. Well, it crosses at the origin. Look back at the equation. I should have seen that right away. If x is 0, it's a true statement, isn't it? 0 equals 0. Sine of 0 is 0. But there are 2 other solutions. I didn't get those. And in fact, they're approximately equal to 1.8955, and it's negative, minus 1.8955. Those are the other 2 solutions. There are 3 in total. Notice the symmetry of this problem. That's an odd function, and hence it's symmetric across the origin. If there's a solution over here, then on the other side there'll also be one. Now, you might ask yourself, how did we do that? Well, we graphed it, and then we found out where it crosses the x-axis. There's a number of ways of doing that. Graphing calculators can zoom in on a certain portion of the picture. So you could zoom in on that crossing point and get a bigger and bigger picture of it. You can look down and see what the value is. But most calculators now have something called a root finding ability. And you can use that button to actually get the precise approximation. That's kind of an oxymoron, but you can get an approximation that is very, very accurate, say to 15 digits or 10 digits of accuracy by using the root finding technique. And of course, good students would say, how does that calculator work? How does it find roots? That's a great question. And students ask me that all the time. And the answer is, well, you can find out the answer by taking a calculus class, because in calculus courses, you learn how to find roots of equations. The technique is called Newton's method, named after Isaac Newton, and it's a method that uses calculus. And the calculators have a modified Newton's method for finding roots to equations. A side note here, I think I told you early on in the course that I was a research mathematician, and my research is in the area of numerical analysis. And in particular, I study something called the Cordic algorithm, C-O-R-D-I-C, Cordic algorithm. And this algorithm is the algorithm built inside calculators for evaluating functions. Let me say it a different way. If you pick up your calculator and punch the sine key for some number, sine of 25, out pops the decimal approximation. How does the calculator do that? How did the calculator get the approximation of the sine function, or the logarithm of something, or the tangent of something? How does it do it? It uses the Cordic method. And if you're wondering what it is, look it up on the internet. It's a fascinating area of mathematical research that's really, really important because it's utilized in graphing calculators. And I'm proud to say, I kind of know how it works. Okay. Let me focus now on something a little bit different. An application to calculus, not quite an equation anymore, but I want to present a graph for you because in the next lecture, I'm going to need this property that I'm about to illustrate. So it's kind of a change in gears here, but I think you'll enjoy it. I want to consider a function that has a very curious behavior, and it's the function sine x divided by x. Let's talk about it for a moment. What's its domain? Well, you can't divide by 0, can you? So the domain is all x except for 0. It's actually symmetric across the y-axis. This is an even function, it turns out. The numerator is odd, the denominator is odd. Odd divided by odd makes an even function. But here's the fundamental question. How does this function behave near the bad point? The bad point is 0. What happens near 0? Well, let me graph it. Here's the graph of sine x over x. And you see from the graph that near 0, it seems to want to be 1. It's getting closer and closer to 1. Mathematically, we write this as follows. The limit as x approaches 0 of sine x over x equals 1. That means that sine x over x gets very, very close to 1 when x gets very, very close to 0. So keep that in mind. It's kind of an interesting graph. You should try to draw it on your graphing calculator. You'll see that it's not defined at 0, but nearby the values are very close to 1. Okay, back to equations. Sorry about that interlude, but I think it's kind of an interesting graph, and it'll come up next lecture. Let's go back to these equations. I'd like to point out that some equations are really easy to solve. For instance, find all x values such that sine squared x plus cosine squared x equals 1. And you'll say to yourself, everybody, all x values, that's an identity. It's true for all x. Or what if I say, find all x values such that cosine x is 2? Cosine x is 2. And you'll say, nobody. There are no values of x. Remember, the range of cosine is between -1 and 1. It's in that sandwich between -1 and 1. Cosine is never equal to 2. Okay, let's do an application. I like to try to do an application every lecture to see the power of trigonometry and in the real world. This application uses an equation of motion of a particle that's moving, and it's only under the influence of gravity. There's no air resistance. So in a sense, it's kind of somewhat simplistic, but the ideas are still pretty important. Imagine a baseball has been batted, and it goes up in the air, and it comes down, say, 300 feet from home plate. So it flies 300 feet in the air, and let's assume that it was hit with a velocity of 100 feet per second. Well, there's an equation that gives the range of a projectile, of this baseball. And the formula comes from physics. And it's equal to range equals 1/32 times the initial velocity squared, and that's usually denoted v sub 0 squared, times sine of 2 theta. Sine of 2 theta. That's a formula for the range of a projectile when there's no air resistance. Here's a picture of our baseball leading the bat at a certain angle theta and going 300 feet. Here's the question. What is the angle at which the baseball left the bat? Now, you could ask lots of questions here. You could be given the angle and ask, what's the range? But I'm doing it backwards. I'm giving you the range. I know how far the baseball went. What was the angle? Well, we can solve it now, and then I want you, after we're finished solving, see if we got the full solution. So here we go. R equals 1/32 times V0 squared sine 2 theta. Again, a formula from physics, a formula that you would derive in a calculus class or a physics class, but I'll just give it to you. And we plug in the numbers. The range was 300. And 1/32 times the initial velocity was 100, so it's 100 squared sine 2 theta. Okay, we've got some numbers there, and we have sine 2 theta. Let's get sine 2 theta on one side, and then everybody else would be 32 times 300 divided by 100 squared. And you can do a lot of cancellations here. Cancel some zeros, cancel some 4s, and you finally get 24/25. Sine 2 theta is 24/25. Now, you aren't expected to know what theta is here. You're going to have to use the inverse sine function here. Generally, in real-life problems, the numbers are not very pleasant, and you have to actually use the inverse sine function. So 2 theta is arcsine, or the inverse sine of 24/25. I'm using that inverse relationship. That means theta is 1/2 arc sine 24 over 25, and then I punched it on my calculator. And in radian mode, I got a certain answer, and in decimal mode, I got the answer of 36.87 degrees, which I think makes more sense. So the angle of the bat was at 36.87 degrees. And if you plug that into the original equation, it's true. That's a good answer. Now, did you notice something here? Something kind of subtle. There's another solution to this problem. You might have noticed this. The angle 90 minus 36.87 is the angle 53.13 degrees, and that also satisfies the problem. There's this angle, and then there's actually another angle up here, the complement of the answer. That's quite difficult to realize, and generally students are never expected to be able to figure out that second solution. Okay, let's turn to a real calculus application. I got this problem again out of a calculus textbook, but we'll be able to answer it with our pre-calculus skills, our trigonometric skills. We've become quite adept with trigonometry, and this problem is very, very approachable with our knowledge of trigonometry. It's kind of a fun problem, and it's indicative of many, many calculus problems where you try to find a maximum value or a minimum value. So here's the problem. Imagine you have one arc of the cosine function. Remember that cosine of minus pi over 2 is 0, cosine of 0 is 1, and then cosine of pi over 2 is 0 again. So that's an arc of the cosine function. And stick inside a rectangle with the base on the x-axis, and it goes up and bumps into the cosine function. And I want to find the value of x, where x is that edge of the rectangle, that makes the green rectangle as big as possible in area. And you can imagine certain values. X could be really, really small, and you'd have a tall, skinny rectangle, wouldn't you? Or x could be close to pi over 2, and you'd have a very flat, short rectangle. Or perhaps, like the one shown in the picture, would have more area. So the question is, what's the optimal rectangle here? Well, let's solve it. This is kind of a fun problem. What is the area of the rectangle inside the cosine curve? Well, the base is 2x, where x is the coordinate on the right-hand side. The base is 2x. How high is the rectangle? What's the height? Well, x goes up and hits the curve. So the height is cosine x. The height is determined by the cosine function. So the area is 2x cosine x, and there's a domain here. X starts at 0 and ends at pi over 2. Clearly, if x is 0 or if x is pi over 2, you have a pretty bad rectangle. In fact, you have a rectangle with no height or a rectangle with no width. But x is somewhere in between those numbers. All right. How do you find the maximum value? If you took a calculus course, you would do it a certain way using calculus skills. But we don't need calculus. Graph this function on your graphing calculator. Here's a picture of it. That's a picture of 2x cosine x on the interval 0 to pi over 2. Notice that at 0 and at pi over 2, the graph is 0. That's because there's no area. And then find the top point. The high point on that graph is the maximum. And it turns out, using a feature of your graphing utility, the maximum area is approximately 1.12 square inches, and that occurs when x is approximately 0.86. By the way, graphing utilities have built-in maximum and minimum solvers. And again, if you take a calculus class, you'll discover other ways of solving these problems. In fact, calculus, one of the great applications of calculus is optimization, finding maximum values, maximum profit, or minimum cost. These recur as themes all over calculus. Great. we've finished sort of a very brief look at equations involving trigonometric functions. Now I'd like to turn to some more formulas. And next time we'll look at formulas for sums and differences of angles. And they won't be as pleasant as we would like. For instance, we will look at the formula for the sine of a sum. What is the sine of x plus y? Unfortunately, it's not sine x plus sine y. So come back to the next lecture and you'll see what the answer really is, and we'll see how also to use these trigonometric formulas involving sums and differences. Thank you very much.